so section 2.2 is organizing quantitative data now. So they're going to give us data that's now numerical that we need to kind of organize it. This is where it gets just a little bit trickier because you might get a wide range of numbers, so organizing isn't always the easiest way. So let's look at this first example. How can we organize just using tables? I pulled this from your book, okay? This data represents the number of customers who arrive at Wendy's during the lunch hour. So they decide that 11 to 1 is the lunch hour, and every day they say there were 7 people that came, 6 people that came, 6 people that came, and so forth. So this is 1, 2, 3, 4, 5, 6, 7, 8. 8 weeks of data for lunch hour arrivals at Wendy's, all right? So what they want you to do, so do you guys agree that it doesn't range horribly? Like, what's the lowest amount of customers that arrived? 1. What's the highest amount of customers that arrived? 11. So that's only a span of 10, right? So that's not hard to just chunk all the 1s together, all the 2s together, and so forth. And so that's exactly what it did, and I just said, you guys can do this, so I'm not going to worry about us filling it out. But since the data didn't range that much up here, they just left all your categories the single numbers, 1 through 11. They counted and tallied how many of those occurred, and they wrote them in their frequency, so it's just like we had on 2.1, or frequency distribution. And then what they do over here, how'd they get all these numbers? They divided by what? The total of 40. Divided frequencies by 40, which was the total. Remember, we had 8 weeks of days, okay? So they showed you with the first example 1 out of 40 because one customer showed up 1 time, so its frequency was 1 out of the 40 days. But down here, 6 happened the most. 11 days, there were 6 people that arrived at lunch hour, so they took 11 over 40 and got 0.275. So it's exactly what we did on the front page with our data, but now it's technically quantitative data and not qualitative. Nothing different. Okay? So then it's like, okay, well, what do we do with this? We said, let's put it in a chart. Let's make it visual. Let's see a graph, all right? So objective 2 is put it into a graph, but what do they have to do? They have to say, oh, well, let's make this really tricky for those stats students. Let's not call it a bar graph. Let's call it something completely different, even though it's exactly a bar graph, all right? So that's what a histogram is, okay? A histogram is just a bar graph for quantitative data. Bar graph for quantitative data. The bar graph for quantitative data. And read the instructions. It's exactly how we would have done a bar graph before. It's constructed by drawing rectangles for each class of data. Okay, that's your quantitative data that you, and the height of each rectangle is either the frequency or the relative frequency of that class. The width of each bar, guys, should be the same. So like you shouldn't group 1 and 2 together and then everything else is singular. So notice that every one is just singular 1 through 11. What's the only difference between this one and this one? Yep. So what we're going to do, this is just a histogram or a frequency histogram if you want to call it that. And this is a relative frequency histogram. The only difference, guys, is our y-axis. The bars are the exact same height. The x-axis, the number of customers, are exactly the same. But instead of going to the whole numbers, 1, 6, 11, bless you, it went to the relative frequency. Okay? So that stays consistent. So whether it's qualitative data or quantitative data, bar graphs are going to be to their actual height or frequency. Relative frequency bar graphs are going to just go to their relative. Okay? All right. So let's go ahead and start talking about the top of page 4. What if our data isn't this compact? Like this was only a span of 10. What if like one day kids were out on field trip, so like 42 kids came? Do you want to have this axis 1 to 11 and then have to draw it way out here to 42? That would be really ugly and tedious and annoying, right? So what we have is with quantitative data, a lot of the times you have to group it, okay? You have to chunk it together to make it not take up a whole page. And that's what we're doing on the top of page 5, okay? So we're organizing continuous data into tables. So there's a lot of hidden vocab words in here, so I'm going to try my best to point them out, guys. So the first one is classes. They are the categories in which data are grouped, okay? They are the width of your bar, okay? They are your width of your bar. So our class on the previous one was just a class width of 1, because we had 1 customer, 2 customers, 3 customers. But once we start grouping them, they're in a class, all right? So say we're taking averages of ages of instructors at Lewis and Clark, okay? So I go around, and you guys agree that we range in age, anywhere from 25 to 82 maybe, who knows, right? So we don't want to have a bar graph that has an x-axis from 25 to 82. So what do? We group them by tens, all right? So notice up here, we just have age ranges, 25 to 34, 35 to 44, 45 to 54, and so forth. You see the pattern there? Okay. So what we're going to do, anyone who's in the age group, so I'd be in that first age range, all right? You throw me in there, I'm in the first class, all right? But the second I popped and turned 35, I would jump into the second class and so forth. So each of those classes are made up of 2 things, a lower class limit and an upper class limit. And I think their names are pretty self-explanatory, all right? What does it mean to have a limit, an edge, or a stop, right? What's it mean to be lower? The least, okay? So the lower class limit is the smallest data value that can be included in a class. So if we're using these groups of classing, all the lower class limits are these younger ones, 25, 35, 45, 55, and so forth. Do you agree with that? Okay. So you have to be in the class, but you're the smallest data value in that class. On the upper end, though, upper class limit, what we have going on here is the upper end, 34, 44, 54, but since our data isn't necessarily discrete, we have to realize that that includes decimals. And guys, I've never told my age in class, but this is me, okay? I am 34. I'm turning 35 in December. So am I exactly 34? No, I'm closer to 35. But I'm still in that first class. Why? Because the second class doesn't start till I'm 35. So realize, even though it says 34, it's 34 to 35 infinitely, okay? So like I'm 34.75 or something like that, right? So 34.75 would still be in that first class. I just, like I said, I don't usually tell my age, but this is a perfect example of where that will fall into place. So it can be discrete or it can be continuous, but it's all right there for you, okay? So upper class limit is the largest data value, but you might have to include decimals. All right, last but not least, class widths are the difference between consecutive lower limits. Difference means what operation? Subtract. Consecutive means what?
Like 1, 2, 3.
One after the other, back to back, right? So, what does this mean? It means if you want to know your class width, how many years of age does the class hold? You take one lower limit and subtract the other. So go up here, 35 minus 25, what's that difference? 10. So even though this stops at 34, that's holding 10 ages. And count them on your fingers, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, right? So I have 10 ages, and so that's what your class width is. But an easy way to do it is just subtract your lower limits. What else can you do? Subtract your upper limits, right? They're all the same width. So whether you do 44 minus 34, you're going to get 10. All right. This, guys, I always mean to do this, and I forget, so cross this out. The pencil's leaving me. We're never going to do it by hand. Okay? All right. So how do we make this happen? How would we construct a how would we construct a histogram of continuous data? So say I go around campus and I ask all the professors how old they are, and we're given all their names. How would we even begin to start arranging them, okay? The first thing you have to do is you have to determine your size of your class width. That's kind of told up here, but on my math lab, in this class, I'll always tell you the class width, okay? I'll always say, make a histogram with a class width of 10. Like, I will tell you. You don't have to make it up yourself. Then select a good starting point, meaning what's your lowest value or what's a convenient lowest number, all right? So usually the lowest value or convenient number lower than that. So say it's our ages and our lowest instructor is 23 and a half. Start at 23, right? It's going to be low, but it's not going to be this awkward half. And then what you do is you keep adding the width to get all the lower class limits. So you actually find the lower class limits first, all right? After you get all the lower class limits, then you know the upper class limits are going to just stop where the other ones started. So if we have 25, 35, 45, we know he has to stop at 34 because this next one started at 35. I'll make it all make sense with an example here in a second, all right? Once you have your classes, you guys can tally the data. How many instructors are between 25 and 34 years of age? How many instructors are between 35 and 44 and so forth? At that point, you can turn it into a numerical frequency, a relative frequency, and draw your graphs, all right? So the example I chose, I stole from the book, is the following data represents the time between eruptions in seconds for a random sample of 45 eruptions at Old Faithful in Wyoming. Construct a histogram to represent the data. Has anybody been to Old Faithful before? Okay. Do you all know what a geyser is? You have? So you actually got to see it erupt and stuff? That's awesome. So what we have is somebody, say you did this, she's like, oh, I wonder how much time is between each of these eruptions.
Oh, they have it actually timed.
Oh, they do it themselves? So these are probably legit numbers then, because I got it from the book, so they're probably real.
When we went, it was like an hour.
Oh, gosh. Oh, gosh, that's a long time. Does that change? Does anybody know if that changes due to season? It's unreal. Okay. So what they did was they sat there for I don't know how long until they had 45 different eruptions, but between each eruption, they had a stopwatch and they were measuring the distance. And so, like, say you come and visit and you're just passing through. It's like, how long do I need to wait before I see one of these guys? Is it an hour? Is it 3 hours? Is it 2 minutes? And so what we're going to do is we're going to gather the data. So if you look at the top of page 6, you guys are so good. You like wait to turn it over. All right? Top of page 6. Remember, this is measured in seconds. I don't know if you want to remind yourself that, in seconds. So this must have been like a certain point in the season, because if you do this, guys, this averages like to 10, 11, 12 minutes, where it's not that hour that she had to wait, okay? So we have 45 data values here. How do we even begin to measure this? Do we really want to make a scale from 695 all the way to 738 or whatever? No. We want to group them into classes, all right? So how do you do this? You first have to come up with your smallest data value. What's the smallest number? And some of you guys are going to be really quick, and some of you are like, oh my gosh, I still don't see it, even though somebody said it. I still don't know what the smallest value is. What's the smallest number you see up there?
672.
It is 672. It's right here, okay? What's your largest data value?
738.
It is 738, okay? Do you guys all trust that you would eventually get there? Just some people are a little bit quick. I was like, 699. Oh, wait, there's a lot more less than that. All right, so this is 738 seconds. Guys, what is that? That's a span of about 70 seconds, so almost a little over a minute. So do we really want to have a single digit seconds as our x-axis? No, so we're going to start grouping them. So the number of classes, it says your choice, because you can say, I only want 2 classes. Maybe you split it in half, or I only want 3 or 4. It's not really your choice. In order for me to grade your guys's, you're all going to have to do the same amount of classes. So let's say we want 7 classes. So if that's true, what are we going to need for class width? I would tell you this, okay? This is going to be told. It's going to be 10. It's going to be a width of 10. What does that mean? It means it holds up to 10 time frames, okay? So if we're starting at 672, it's going to go from 672 all the way up to 681. It's going to have a chunk of 10 seconds. All right, so now what we're going to do, this is going to be kind of awkward because normally I would do this vertically, but just to save room, I'm doing it horizontally. Let's come up with all of our lower class limits. And you're like, what the heck was that again? How we do it is we select our starting point, usually the lowest value, and then we're just going to add the width to get all of our lower class limits, okay? So what was a good starting value? 672 is not horrible, but what would be prettier? 670. Do you guys agree like jumping by tens is a lot easier than 72, 82, and so forth? So let's start at 670 for our first lower class limit. But if it's a width of 10, where would the next class start at?
689.
680. You are doing the whole class, which that's perfectly fine, Jocelyn. I'm just doing the lower class first, and then I'm going to go back. And then what's going to be our next lower class limit? 690. Does everybody see what I'm doing? How many times do I need to do this? Well, how many classes do I want? 7, right? So we're going to have 700, 710, 720, and 730. And if you need something, because you're like, I don't know what she's doing, or you get it now, but then later on you're like, where did these numbers come from? Label this as a convenient low number, right? Because what was our lowest number? 672. So 670 was a little bit more convenient. And then what did we just add each time? Right? Which was our width. Just so you kind of have a note, like, where did Molly come up with all these numbers? I have no clue. All right, so then Jocelyn was already doing it. If we know we're going from 670 and then our next class starts at 680, where is the upper class for that first class? It has to stop at what number?
79.
79, okay? So again, it's hard to see because I'm doing it horizontal. This is the first class. This is the start of the second. So he has to end right before he starts. So where is he going to end? 679. So any seconds between 670 and 679, we would tally, and they would go into that first class. You guys see that? So all of our classes are starting with these nice whole tens. The first class will start with 670 seconds, but once we jump up to 680 seconds, we're going to go into the second class. But if the second class starts at 680, he must end at 679. And guess what the pattern is? 10, 10, 10, right? Because if he's going to start at 690, where must he end? 689. You got it. And what should I say? Stop before start of second class. Will that make sense for you later on? I'm trying to think. So we had to stop at 679 because we had to stop before the start of the second class, 680. Maybe put that in parentheses. Is that a good note for later, like why we picked that? All right, so we did it. And guess what? We could have cheated this whole time. Look what I have at the bottom half of this page. The frequency distribution that goes with this data is already tallied and already has the relative frequencies, okay? But look how their chart matches exactly what we said was going to happen. The perfect starting point was 670 because it wasn't that weird 672. I told you I wanted a class width of 10, so each class lower limit went by 10. And since all of them went by 10, the upper limits had to stop one less. So that's 679, 689, and so forth. So what did they do for us? Thankfully, you guys don't want to look through 45 numbers here, right? They went and saw how many numbers are between 670 seconds and 679. Can we find those two numbers? Well, which one for sure? 672. What's the second one? 678. Right there, okay? So those are the two that come in that gap. Notice none happen to happen in the 680s, okay? So you just put a 0 there, that's fine. Do you completely ignore it and squish it? No, you still have a spot for it, so we're still gonna label 680 to 689. It just won't have a bar that goes up. It'll just be blank as we jump from 690 to 699 and so forth, all right? How did they get their relative frequencies? Well, they said somebody sat there for some reason for 45 different eruptions. And so what was our total number? 45. So what did they do to get all these numbers? They took all these numbers and divided them by 45. So what's the point of this? Because if you're actually at Old Faithful looking at these geysers, you might ask yourself, on average, most of these have what kind of time span? This one right here. Okay? Do you guys agree that's your highest? 24%? Okay? And even this, right? So the fact that two of the higher ones are kind of towards the longer time frames, you might say, okay, well, if we just wait 11, 12 minutes, we should be able to see one. Where if maybe it was shorter, you might see a couple or whatever it may be. And so we have a nice way to organize it. Notice at the bottom, guys, that we can use these numbers and create a beautiful histogram, right? This is a this is just a frequency histogram because all they did was use these frequencies up here to draw the heights of the bar. But notice most of them are in this time frame, right? So you know that you're probably going to have to wait more than 10 minutes or so to see those eruptions. Notice they do a good job of labeling. Not only do they tell us what these numbers are, which is time, but it tells us what the time's measured in, seconds. There's a couple of things I want to point out. Notice the bars are the same width. All the bars are the same width. And all the bars share sides, right? There's no gaps. Bars share sides. Why am I pointing that out? If you flip back to 2.1, where we looked at those bar graphs, what did you notice between all those bars? There's gaps because it's qualitative data, right? The neck has nothing to do with the elbow, has nothing to do with the back, so we're separating them. But you know what this line is right here? This is the difference between 699.9999999 seconds and 700 seconds, right? We have to have that. Remember me being on the edge of 34 and 35? I would be one of these sides. We have to share it. This one stops at 699.999, but this one starts at 700. We have to share sides, okay? So make a point of that when you have to draw one by hand. Are there any questions on that, guy? All right, let's do the flip of this real quickly, and then I'm going to stop the recording and start it over again because I'm getting kind of long. Why might drawing a histogram not always be the best option? Okay, so we chunked it together. We have these heights of the bars. We know which ones occur the most. But why might not that always be the best? And I'll kind of hint to you guys. You guys keep your page right there. Let me flip back to here. Looking at this bar graph. So say you don't have this. Looking at that bar graph, how many times did 615 seconds happen? No, I meant 7. Good, Don is right. 715 seconds. How many times did 715 seconds occur?
You don't know.
So you're telling me this whole bar is filled with 715 seconds? No. That whole bar spans from 710 to 719. Do we know how many times 715 shows up? No, right? We know its class is up to 9, but we don't know itself. So once we make a histogram, guys, we've grouped data and we've lost individual data values, okay? This is a lot different than this. You can tell me here, how many times did 715 show up? You could go around and count it, right? But once you have this, you lose individual data values. And that's what I want you to write at the top of page 7, guys. Once a histogram is made, raw data are lost. Raw data are those individual numbers, okay? And like I said, if I ask you a question, how many times did 17 or 715 show up, you wouldn't be able to tell me. You can say, okay, its class showed up 9 times, but I don't know how much 715. Once a histogram is made, raw data are lost. Remember, data is plural, so that's why I put R. It sounds weird, doesn't it? Raw data are lost.